Okay, so now we're going to put all the ideas that we had discussed to applying it to calculating the pH of acids. We're then gonna follow up with calculating the pH of bases. Starting with acid, this is the way you want to approach how to calculate the pH of acid. First thing is you want to write all the reactions that produce H plus. So even water itself could produce H plus. If you have multiple acids that's mixed together, each one of those acids can produce H plus. So you want to write all the reaction. And then the next thing is you want to make sure you rank the reaction from the largest to the smallest K to prioritize certain reactions over others. And the reason we do that is because some reactions produce so much H plus that even though you might have other reactions that also produce H plus, the first reaction dominates so much that you can ignore all the other reactions. Most of the time, the reaction with the largest K will determine how much H plus you have and therefore determine the pH of the solution. In the examples that follow, you'll see how some of the smaller K reactions may be ignored in determining pH. All right, now let's talk a little bit about number three there, the mathematical part of it, which is how do you solve these problems? Well, you're going to go with the methods of equilibrium that you learned in prior chapters. We're going to use the ICE table, and then when you are able to, you're going to use either a small or large K assumption. And we'll do examples where we can use one or the other assumption. And as always, you want to check your assumption to make sure that it's allowed. So there's that 5% error cutoff that we want to keep in mind. And then lastly, if assumptions are somehow not possible, then you have to use your direct methods, which is either a quadratic formula or successive approximation. So we're going to start with this example right here. It says calculate the pH of 0.01 molar HBr. Step one, I would write all the reactions that produce H plus in this solution. So if you think about a solution of just HBr, keep in mind that's HBr aqueous, so therefore there's two things in there. There's HBr and there's water. HBr is an acid, so it produces H plus. Water can act as an acid, it's amphoteric, so it will also produce H plus. So you see, I've written two reactions. One is the HBr reaction, the other one is the water autoionization reaction. Then the second step is to rank the reaction. We have to determine, based on K value, we know from the Ka table that HBr is a strong acid. So it's one of the ones at the top there that's marked in blue. So HBr has a K of 10 to the 9. But anything above there that's in marked in blue means that it's going to go to completion. So in this case, we would say completion for HBr. Very important because Ka is much greater than 1. Now, what about water? Well, that reaction that I wrote there for water is the autoionization reaction. So the K for that reaction is our Kw, which is 10 to the minus 14 at 25 Celsius. So now we have two reactions. One has a really large K, the other one has really small K. So we're going to prioritize by dealing with the larger K reaction first. I set up my ICE table on the left, as you can see, and I have the initial concentration of HBr being 0.01. And of course, at the beginning, I don't have any products yet. If it's a strong acid, how much of it is going to turn into product? The answer is all of it, right? Because the K is much greater than 1. So if we think back to that large K idea, anytime you have a really large K, that means that all your reactants become product, and so all the reactants are used up. That's an assumption. We would say that at the end we have close to 0, but not quite 0. But it depends on what we're looking for. In this case, we're looking for pH. So all we care about at the end of this problem is finding out how much H plus concentration. We're not being asked for the HBr. So yes, the HBr concentration is not 0, but it's not relevant also to our question. So we can say it's about 0, and we can say that the concentration of H plus and Br minus at equilibrium are going to both be 0.01 molar. Now, once we have that, we can stop there and calculate the pH, right? And the pH would be negative log of 0.01, and it will be 2. Okay, but if I do that, then I'm ignoring how much water contributes, because water also produces some H+. So let's see how much H+ comes from water. So I'm going to set up my ICE table again now with water, okay? Now look at the numbers I put there. I don't put anything on this side right here, because that's a liquid. So even though I actually have some water in there, there's no reason to put any numbers in there because it's not going to go into my K expression anyway. But what I will do is fill out the product part because they're both aqueous. So I put 0.01 and I put 0 here. Now, why did I put 0.01 for H plus? Because the way you analyze this problem is sequential. So when you have that first reaction happen, you assume that at the end of that reaction, you have 0.01 molar H plus. So now when you analyze the second reaction, which happens after the first reaction, you already have 0.01 molar H plus floating around in your solution. So that's the reason why I put 0.01 there. In reality, is one reaction occurring after the other one? That's not a question of equilibrium, but a question of rate. Which one happens first? They both happen very fast that it's sort of irrelevant to talk about the actual speed. But when we're solving these kind of problems, mathematically, it's very helpful to analyze them one at a time, to take one reaction which has the larger K and then to go to the next reaction that has a smaller K. And that's what we're doing here. So if we go about it that way, then
our change is still going to be plus X.
Why still plus? Because we don't have any OH minus, so we don't have a product, right? If we don't have a product, that means we're going to make some product. And so at equilibrium, what we have is 0.01 plus X for the H plus, and then just X for the OH minus. We set that up equal to the KW expression, which is this one right here. KW equals H plus times OH minus. The H plus is 0.01 plus X. The OH minus is just X. Now here's the simplifying part. Notice that 0.01 plus X can be assumed to equal to 0.01 because this is a really small K. Whenever we have that situation, as we learn equilibrium, we can make that assumption.
So the equation simplifies to 0.01 times X.
Then X can be solved to be 10 to the minus 12,
which is equal to the hydroxide ion concentration.
Not really relevant to our question because we're not actually being asked to solve hydroxide ion concentration, we're just being asked for pH. So then the question becomes, okay, so let's calculate the total H plus then. The total H plus would then be the H plus that is from the strong acid, which is the 0.01, and then the X, which that's the one that comes from water. Well, we just found out that the X is this much, 10 to the minus 12. So if you want to calculate the total H plus concentration for this solution from water and HBr, what you have is really 10 to the minus 2, that's the one from HBr, plus 10 to the minus 12. Well, you know that when you add these two numbers together, pretty much just get 10 to the minus 2, right? Because that's 10 orders of magnitude greater than 10 to the minus 12. So therefore, the final concentration is really 10 to the minus 2 molar. So the pH is exactly what we calculated earlier when we ignored water, which is just minus log of 0.01, which is 2. Here's an important lesson. When you have something with water, the ionization of water can be ignored. We will talk about what situation where we have to worry about the autoionization of water, but generally speaking, you can skip doing this whole step right here. You can just not worry about it because the contribution of H plus from water is so small that it's not going to make a difference to your final pH value. Let's take a look at the second problem here. The second problem asks us to calculate the pH of two types of acid, 0.5 molar HF and 0.05 molar HF. I have space here for the first one. I'm going to do the other one on another page. But we start the same exact way. We have our HF, we write out our reaction. It starts with a half molar, that's the first one. 0, 0, minus X plus X plus X, so we have this for equilibrium. And then the expression for the equilibrium constant, of course, is products over reactants, so it's just X squared over 0.5 minus X. But if you look up the Ka value of HF, it's right here, hydrofluoric acid, and 6.6 times 10 to the minus 4. So it's a small k, which means I can say that that's 0.5 minus X is roughly equal to 0.5. At least I can try to see if that works, right? Because that's an assumption. I can check it at the end. If I do that, my X, after I solve it, ends up being 0.0182 molar. Now, if I check this using my test that I did before, which is just to take 0.0182 divided by 0.5 that I'm comparing it to and then multiply by 100%, I find that this is roughly equal to about 3.3%, which is below my 5% cutoff. So therefore, the assumption is acceptable. So my final pH value is just the negative log of that number, and it's 1.74.
I want to point out the important difference between these two problems.
In this ice table, I had minus X plus X plus X. In the previous ice table with HBr, I had minus 0.01 plus 0.01 plus 0.01. And so what's the difference between these two acids?
Why did I use all of the initial acid in HBr and only X in HF? Let's go back.
To that Ka table. Anything that's blue is strong acid there in the top. So when that happens, you assume completions. Everything that you put in becomes H plus. Once you're below here, like right here, the hydronium line, then all of these guys here, they're all weak acid. So by definition, they don't get fully converted into H plus. A lot of the weak acid sticks around. And so you have to calculate it out. And that's why I use
X
to represent the quantity of acid that is dissociating. Right, so minus X is some amount of acid that dissociates, and then we can calculate
what it is.
Now let's take a look at that second problem, which is 0.05 molar HF. I worked out this problem here, and you can see that the setup looks pretty much identical to the problem I just did with half a molar. 0.05 now, 0, minus X plus X, and then the setup at equilibrium. And then I use exactly the same K expression for HF, and the same value. And I still use the same assumption right here, which is to assume that that 0.05 minus X is roughly equal to 0.05. If I do that, this is the answer I got. Now, here's the problem though. When I do my check step, which is just to take the X value divided by the initial concentration, the number that I'm comparing it to, which is this number right here, I end up getting 11.5%.
That's too large.
For what I want my assumption error to be. So when I have this type of situation, I have to just solve the problem directly using quadratic or successive approximation. If you look at the equation you're trying to solve, which is this one right here, you can cross multiply that denominator with the Ka value and then write it out in the form of quadratic equation, ax squared plus bx plus c equal to 0. And that's what I have here at the bottom. Okay. So once I have that, I can use the quadratic formula to calculate out my x1 and x2. I find my x1 to be this number, my x2 to be that number. Because it's a negative number, it's not a correct answer because concentrations are at the lowest is 0, but it's never negative. So therefore, only the top answer is correct, and that should be my H plus concentration. And then to get my pH, all I need to do is take the negative log of that number, and that gives me a pH of 2.27. Just to give you a little feel for how pH changes as a function of concentration, earlier we had calculated
The pH
of a half molar HF, and that was
1.74.
Now we have decreased that concentration by tenfold to 0.05 molar HF, and now you can see that pH has increased, so the solution is less acidic now. It's still acidic, but it's less acidic compared to that higher concentration HF. Okay, so that's the second problem. So again, want to highlight a few things there, which is that when you calculate weak acid, it's different compared to strong acid. When you have different concentration, sometimes your assumption method works, sometimes it doesn't, so you have to be a little careful. You might have to do quadratic in some problems.